So welcome to this lecture. In the last lecture, we talked about set theory a very little bit. We saw what belongs to means. Although we didn't give definition of belongs to, we just gave a linguistic simple in the English language, English description of informal description, I would say, of this belongs to. Later we will concept this idea further, right? And then we saw a concept of union, and union was about putting two set given those elements together into one set, right? You have a set of people, let's say we have a set n. A set n is set of people, all the people living in Nepal, right? And then we have set a, set of all the people living in America. So you have two sets, set n, set a. Union is what we're going to do. It's going to take all the people of Nepal and all the people of America, and it's going to put in one set, right? All the people into one group, and that is called union. Union is taking two different sets, two different box, take out all those elements and put it into one box, right? Are you getting what I'm trying to say? Union is about, you have given two box, those box A and box B. Box A have okay, maybe yes. So box A and box B could have different elements. A box A has, let's say, some chocolates, fruits, and let's say some sweets. Okay. Box B has, let's say, money, some coin, right? Some dices. Okay. What A union B gonna do? Take this box A, open it. Take this box B, open it, and take out all those, whatever the box A and box B has, and bring another box and put it all into it. That is what union is. Then we saw concept of order of a set, right? And we said the set has no order. You can arrange the element of a set in any way you like. It's up to you. It's up to us. Whatever we want to do with those elements, right? So a set has no order. So a set with three elements, three number, let's say 1, 2, 3, is not different from 2, 1, 3. They are same, right? Because order does not matter. Now there is one more concept, which is a repetition of element in a set. What is this? Well, you have to say that set theory has this idea that if a set contains same element twice, then you can throw one away. You don't have to put 2 1 into one set. Let's say there is a number 1 and we have a set, and the set has two elements, which is 1, 1. So what set theory is saying that you don't need extra 1 because they are the same one. You see? What about 2 apple? Apple, apple. Set theory says, well, it is apple, throw away 1. So we have 1 apple, just apple. So there is no labeling going on in set theory. Set theory does not recognize two different objects even with same label, right? Set theory does not distinguish between between same elements. It cannot. It says they are same, right? Even if you have, let's say we have uh, two pen. This is the pen. Now suppose I have this pen. Let's say it's a member of a set. I have a set, and in the set I have this pen, right? Suppose I bought one more pen, the same pen, and I'm going to put this both pen into one set. The set theory is going to say that they are same. You don't have to put twice, throw it away. But then what you may think, we may think, okay, it's fine. Of course, they are same pen. Well, but they are two different objects. I mean, they are two, not one. We have two pen. Even they are same pen, we have two pen. So set theory, until we specify they are different, the problem it gets that later it will make mistake. Set theory starts to make mistake while counting on cardinality. Well, suppose what I'm trying to say, we have this pen. Now I bought one more pen, the same pen, and I'm going to put in a set. Now I will ask you, what is the cardinality of the set? It means how many elements I have in that set. Well, I have two pen inside the set, even though they are same, but I have two. But set theory says no, you have one, and that is the problem. Right? That is the problem. Human being, even say they are same pen, this is same color, same structure, but they say they are different. They are two pen. Set theory does not do that. Even if you have, let's say, a number 3, and if you put in a set 3, set theory is going to say they are same 3. What is the difference? Throw it away, 1. You put just 1 3 into the set, and that creates the counting problem. So we invent a different technique called labeling. We label the object. Even they are 3, even this is the pen, we call it pen 1 and pen 2. Now it is become clear to the set theory that okay, they are different. Otherwise, without labeling, set theory gets very woozy. So this was about a repetition of element, how set theory discard if same element repeat twice or thrice. You cannot repeat element and put it in a set, no. And then we saw order does not matter. Then we saw union. Now there is a next relation, and the relation is called intersection. What does it do? Well, intersection is like this. Suppose you have a box, right? This is a box. This box contains let's say 5 objects, right? This set contains 5 objects. It has a mango, it has a phone, it has a chocolate, it has let's say a doll, and it has a coin. 5 things. Set B contains only mango. That's the box B. What intersection gonna do is going to take both box, open it up, and see what is common in both box. What is that thing that is inside box A and box B? Well, it's mango. So it's going to take out mango and put it in a one box. Now are they going to repeat? Are they going to take out this mango from this box and this mango from this box? So you got 2 mango and put it in a set. Well, no. Because set theory says they are same thing. So throw it one away. Put it in a one box. So this is what intersection is. Intersection means take what common in both box and put it in a one box. Right? Okay. Let's do it formally, and we will define it through belongs to, because that is the only symbol we have in set theory. Everything we construct is from belongs to. So let's define it using belongs to, what intersection means. Okay, so intersection. Union has this symbol, Intersection is just inverted U, this, right? Maybe I should make it more generally. Okay, this is intersection. Okay, now how this is defined? Well, for all set, this is similar for all set A and AB, there exists intersection such that A intersection B is equal to define. What it is gonna do, take all those element X such that X belongs to A and X belongs to B. Here is AND. In the union definition, here it was OR. You can see here it is OR, right? It's OR, but here it's AND, right? Now we will do an example, right? The example could be, let's see here. What is the example? Well, the example is, take a set. Let's say we have a set A, and that set is equal to 1, 2, X, right? And now we have another set which is B, and this B is equal to, what should we take? Well, let's say 1, 5, apple. That's a legitimate set. Now what we're gonna do, we are going to define intersection. So A intersection B is equal to, what does it says? It says choose X from this. X means, well, we will get confusion. Let's say put it Y. So it's going to say choose X. X means element, and those element, choose X from both element, both set, and those element should belongs to both set A and B. Well, can we choose Y? Well, no, because Y only belongs to A, Y does not belongs to B. Can we choose 2? No, because 2 belongs to set A, 2 does not belongs to B. Can we choose 1? Well, 1 belongs to A and 1 belongs to B also, so we can choose 1. Can we choose 5? 5 belongs to B, does not belongs to A, so we cannot choose. What about apple? We cannot choose. Apple only belongs to B, it does not belongs to A. So now we close the set. This is unnecessary comma. That's all. A intersection B, we got 1, right? What about this one? A equal to, let's say we have A, B, C, and B equal to, let's say we have X, Y, G, right? What is A intersection B? Can you say what it is? Well, we have to choose all those elements that are in set A and set B. Anything is common here? Nothing is common. So what comes here? Empty. Nothing. It's called phi. You see that symbol? It's called phi. Now what is phi? Phi means empty, right? And here we got phi. A intersection B equal to phi. It means nothing is common. The set is empty. It means set is empty. Alright. The phi is the notation for there is nothing common in between both sets. So it is empty. The set is empty. Okay. So now remember, phi is not equal to 0. Okay. Because a set just containing phi and a set containing a number 0, they are different objects. Phi means empty, there is nothing in between this bracket, but here it's 0 here. So it's one element in this set. There is one element, right? For example, here it is 3 element, 1, 2, 3 in this set, right? For example, here it is 4 element, 1 2 3 4 in this set, right? Here there is no element, empty, but here it is one element, 0. There is one element. Or you can say another example of one element is a set with containing 1, or set with containing let's say a letter. It is a set, it has one element, it has one element, it has one element, it has no element, it is completely empty, right? Now this set is completely empty. This is called singleton set because it has single element. This is not singleton set. Phi is not element. Phi is just a representation that it contains nothing. We can also represent this set just like this. Phi. That's all. It means empty. This is also empty, right? Now here we come. This set ABC given A, XYZ is set B. Intersection means what is common between them? Well, nothing is common, so phi. The set becomes empty. A intersection B is empty set. It is completely empty. It is void of any element. It has no element in this set. Okay. Now, the third relation is called complement. What is complement? The notation is given a set, let's say S, given a set A, then complement of S is, right? Given a set S, then complement of S is defined as follows. What is the notation of complement? Various notation. We can choose S and the bar on top of it, or the other notation is S and put C, right, on the head at the right corner, or we can say S and a dash like this, or we can say this symbol, this is like L, not L but yes, like a horizontal bar then a vertical bar, and S, it is also complement. So we have many different kind of symbol for complement, right? So it is defined as, what does it contain? It contains some element X such that X, remember we have to define everything in belongs to, using belongs to. X does not belongs to S. This is what means. This is what it means, right? Where we have to also make clear that this S is a defined given a set S, then complement of S is defined as follows, which is this one. But we have to make one more thing, which is the idea of universal set, right? Universal set. Universal set means a set that contains a set. Universal set is like a, how do you say, we have a universal set U and all the sets are subset of this universal set in the given framework. Okay, maybe I should stop here and we will pick it from here in the next lecture.